Welcome to Waidsum Academy. Today we're looking at physics, chapter 15, simple phenomena of magnetism. So today we're looking at magnetism. Without much wasted time, let's begin. You can see this tray as it moves through the tray track. The tray uses magnetic effect to be able to move what we call the maglev, to be able to move in the tray track. Okay, first of all, before we talk about the applications of magnetism, such as in maglev, let's quickly take a look at the history, the stories. How did we discover the magnets? How did the world come across the magnet? It's a very long time ago. Let's say like about 1200, like the year 1200, somewhere around here. This is when we discover some stone rocks called the love stones. The love stones, we found that the love stones, it's able to attract any magnetic material, certain magnetic material like iron. The love stone was able to attract iron. So this is a diagram of a love stone. So we discovered that if you bring any magnetic material like iron, like paper clip, okay, like scissors, like nail, towards these love stones, they've been attracted. They can be attracted to this love stone. So this was how the whole stories of magnets started, like 800 years ago. So these are the whole story of magnets started and how we started shaping this stone in the form of magnetic bar, so on and so forth, that you have today. Okay, so this is the history, a little bit history of how magnets started. Now, magnets attract magnetic material. This we know, right? Even from our basic science, that magnets, they attract magnetic material. Now, the magnetic force exerted by a magnet can attract any magnetic material. Remember, magnetic material is not only metals. We don't just see a metal, we say it's a magnetic material. This is one of the misconceptions a lot of people have. So once they see a metal, they think all metals are magnetic material. No, in fact, most metals are not magnetic. They are not magnetic materials, okay? Magnetic material, we go to identify them like steel, iron, nickel, cobalt. These are the four common at this level, okay, for this level of study. These are the four common magnetic material: the iron, the steel, the nickel, and the cobalt. These are the four common magnetic material. Okay, they are metals anyway, although they are metals, but not all metals are magnetic material. For example, copper is a metal. Okay, aluminum is a metal. Sodium is a metal. All these ones, they are not magnetic material. They are not magnetic. So you cannot, because something is a metal, you say, oh, they are magnetic material. Not all metals you bring towards a magnet that can be magneted or can be attracted by the magnet. So we're going to take a look at this. So I think now we understand the difference between magnetic material and non-magnetic material. Okay, so we say magnetic force is exerted by a magnet can attract magnetic material. When you bring a magnet towards a magnetic material, it can be attracted. It can be attracted towards the magnet. Okay, whereas a non-magnetic material cannot be attracted towards the magnet. Now let's take a look at the difference between magnetic and non-magnetic material. Okay, well, the major difference is the ability to be attracted by a magnet. The major difference is the ability to be attracted by a magnet. So a magnetic materials are materials that can be attracted to a magnet. Why non-magnetic materials are those materials they cannot be attracted to a magnet. Now let's take a look at an example we've itemized already. I think we mentioned them already. Okay, we measured these magnetic materials. We say steel is a good example of a magnetic material. Iron is a good example, another example of a magnetic material. In fact, iron is used for making temporary magnet because it can easily be magnetized and it can also lose its magnetism after a short while. Okay, and while steel is used for making permanent magnet. Why? Because it's very difficult to get magnetized, and it's also very difficult to lose its magnetism after it has been magnetized. So we say steel is used for making permanent magnet. Steel is used for making permanent magnet. Why? Because it's very hard to magnetize, very difficult to magnetize, and also difficult to lose its magnetism after it has been magnetized. So we say steel is used for making permanent magnet. Magnet, right? And then, whereas iron is used for making temporary magnet. Iron is used for making temporary. So what is a temporary magnet? It's a type of magnet or material that can easily be magnetized and also easily lose its magnetism once you take out the magnet or the magnetic substance, or you take out the magnet. Temporary magnet. Okay, so this is the iron. Iron is used for making temporary magnets, while steel is used for making permanent magnet. Now, cobalt is also a magnetic material. Okay, it can be attracted to a magnet. And nickel, same thing. Nickel, also same thing, can be attracted to a magnet. So, like I said, other metals like aluminum, zinc, sodium, magnesium, those ones, they are not magnetic material. They cannot be attracted by a magnet. So you must know the difference between, not just you just see a metal, you say, these are the famous ones for IGCSE, for Cambridge IGCSE, at IGCSE level and A level. This is what you need, okay? At IGCSE level and A level and OSMAT, okay, this is what you need. And even GED, okay, this is what you need. Is that okay? As magnetic material. Now, non-magnetic material, copper, even though it's a metal, it's a non-magnetic material. Wood, like wood from the trees, obtained from the trees, they are non-magnetic materials. Plastic you use at home, they are non-magnetic, meaning if you bring a magnet to it, it will not be attracted. If you take a plastic cup and you bring a magnet, it will not be attracted. The magnet cannot attract a plastic cup. Neither will the magnet be able to attract a wood. Neither will it attract a brass, even though this is a metal. Even though this brass is a metal, copper is a metal. You can see we gave two metal example here, and we gave wood and plastic example. Even ceramic, you can write ceramic, glass, all these are non-magnetic material. You can write them here as more examples for non-magnetic material. Okay, let's move on. Now, we said this property of magnet is useful when we are separating magnetic material from non-magnetic material, because we already know, especially in the scrap yard, when you use electromagnet. In scrap yard, we use electromagnet to separate magnetic material from the dumps in the dump site from non-magnetic material. So this property of ability for a magnetic material to be attracted by a magnet is one of the reasons that enable us to be able to separate magnetic material from non-magnetic material. Now let's take a look at the poles of magnets. And we say the poles of magnets, they have the strongest magnetic force. Okay, meaning the stronger, if you take a magnet, this is a magnet, this is a horseshoe magnet. This one you see now is called horseshoe. It's called horse. It's called horse. It's called horseshoe magnet. Horseshoe. Horse. Okay, the horse, the animal horse, that's the name we give it. Horseshoe magnet. This one. Okay, it's called horseshoe magnet. Now, the poles are the edge. These are the edge. They are called the poles. One is north pole, one is south pole. You see that? Now, if you bring a horseshoe magnet towards nails, a nail is made from iron and they are magnetic material, right? So they are magnetic. These iron nails are attracted to these poles of the magnet. They are attracted because the magnetic poles is where the magnetic force is strongest. The poles are where the magnetic force or magnetic attraction is strongest compared to every other part of the magnet. Okay, so when you bring them here, they will be attracted at the poles. They will be attracted to the poles. Now we say the end of the end of the magnets are also known as the pole. This end, like we said already, they are also known as the pole. This place. These are called the pole. The end of the magnets are also known as the poles, right? They are known as the poles. Now, when we move a magnet close to a pile of iron or pile of iron nails, like you see here, you see a pile of iron nails. You move a magnet close to it. What happens? You see the iron nails are attracted to the poles of the magnet. You can see the iron nails are what? They are attracted to the poles of the magnet. They are attracted. See some of them be attracted here, and some of them be attracted to this pole of the magnet, as we see in this figure 50.2, right? Now the poles are where the magnetic force is strongest. These poles is where you have the strongest magnetic force. The poles are where the magnetic force is strongest. So you can see this subheading is there. The poles of magnet have the strongest magnetic force. And we've used this kind of like a small experiment to show that you bring you bring the whole magnet, they will be attracted to the poles, to this end of the magnet. this iron A will be attracted to this end of the magnet because that's where the magnetic field is strongest. That's where the magnetic field is strongest. Now let's go to a freely suspended magnet points to the north-south direction. Now you take, let's say you take a woody support, and then you bring a magnet, you tie it on a rope, and you use something to hold it so that it will be free to rotate. You use something like handkerchief or a rope to handkerchief or rope to a paper to hold this magnet, okay? And then you freely let it slide to rotate. So a bar magnet always points in the north-south direction when it's suspended freely. You suspend it, you let it to freely rotate or freely move. Then, as it rotates, it will eventually come to a stop in a north-south direction. You can bring a compass needle to check. You will see that this is the direction of the north. The direction where this bar magnet is pointing is the direction of the north, and this other direction is the south direction. So when we let a bar magnet to freely rotate, to freely move, in a suspended case, you suspend it and you use any woody support, and you let this one. So use woody so that it will not be attracted. There will be no force of attraction. Because if you use an iron or steel here, if you suspend it here, there could be some force of attraction between this magnet and this magnetic material. So we use a non-magnetic material. We suspend it on a woody support like a ruler or a pencil or whatever, something that is non-magnetic, and you let this paper stir up. You let this paper to stir up. So then you allow this one to freely rotate, and it will eventually settle in the north-south direction. Now this is because the Earth behaves like a giant magnet. The Earth behaves like a giant magnet. And the magnetic force exerted by the Earth causes a freely suspended magnet to point in the north-south direction of the Earth. So this one is pointing towards the north-south direction of the Earth. So which means if you draw the Earth, the map of the Earth, or what you call the Earth, this direction will be the north. The direction where this north pole is facing will be the north of the Earth, and this one will be the southern part of the Earth. This way will be the southern part of the Earth. Okay? So whenever we suspend a bar magnet, it will rotate and settle in north-south direction. Is that okay? Okay, now let's move on. Let's go to what we call the like poles and unlike poles behavior. Let's see what happens to like poles and unlike poles. This one is same with when we do electric charge. We say like charges repel or like charges attract. Similarly, in poles, we say like poles we repel, or like poles we attract. What do we mean by unlike pole, and what do we mean by like pole? Or like poles is like if I bring a knot of a pole to another knot of a pole, what will happen? They will repel. There will be a force of repulsion. There will be a repulsion force. If you bring a knot and knot, they will repel. These two magnets will repel each other. They will repel each other. Let's say this is a magnet. These two magnets will repel each other. Here is the north and here is the south. Okay, if you bring north to north, if you bring north to face north, they will repel each other. They will not attract. They will repel each other. Okay, they will not attract. They will not attract. Okay, they will repel each other. That's what we call like pole, repel. Like pole will repel. But if you bring a like pole, they will attract. If you bring, let's say for example, here is north pole, and here is south, and then you bring another magnet, but this time around you make the south to be here. Here is the south pole for this one, and here is the north pole. Then you see these two magnets will attract. These two magnets will attract each other. These two magnets will be attracted to each other. Okay, this one will be attracted to this one, while this one will also be attracted to this one. These two will be attracted to each other. Okay, so that's what it is. Now let's suspend for clarity, let's suspend a bar magnet that is made to freely rotate, and we bring a like poles and a like pole towards it and see the behavior, what will happen. So when we bring two like poles, let's say two north poles or two south poles to each other, like this north, you see here, like this north pole and this north pole, they will repel. There will be a repulsion force, meaning they will move away from each other. That's the meaning of repulsion force. They will move away, north and north. They will move away, like laws of nature, like man and man. See, man cannot marry man. They will repel each other because they are like poles. They are like humans. They will repel each other, right? If similarly, if you bring south towards each other, you bring the south pole towards the south pole, they will also repel each other. Okay, but if you bring a north pole, freely suspended north pole, and you bring a south pole, which is the opposite pole to it, they will attract. There will be a force of attraction. This one will be drawn near to this. These two will be drawn closer to each other. This one will be drawn near this one, and this one will also be drawn near this one. So that's what you see here, attraction between the two, north and south. That's what we mean by alike poles. Alike. North is and south, they are alike. So when you bring alike poles, two alike poles, they will attract. That's the first law. Second law is when you bring like poles, they will repel each other. Like poles will repel each other, and alike poles will attract each other. Now let's go to induction. Let's go to magnetic induction. Okay, what is induced magnetism? Let's talk about induced magnetism. Induced magnetism is just to transfer the property of a magnet to a magnetic material. Ability to transfer magnetism or magnetic behavior or magnetic force into a magnetic material. Let's say a nail or a paper clip. If you take a magnet and you bring it close to magnetic material, it will attract magnetic material. The magnetic property will be transferred to this first paper clip. And this first paper clip will also clip another one. So this second one is not touching this. This second one is not touching the magnet. You see this second paper clip? It's not touching the magnet directly. It's just touching the first paper clip that was attracted to the magnet, which means this paper clip has gained magnetism. It's carrying the magnetic property or magnetic force. That's why it's able to hold on to the second one. And second one is able to hold the third one. The third one is able to hold the first one. Why? Because magnetism has been induced. Okay, from this magnet, it has transferred magnetic property or magnetic force to this first one transfer to second transfer to third transfer to fourth. So we say this is having an induced magnet. This has become an induced magnet, this first paper clip, or the first paper clip that has been plunged directly to the magnet. They are having what we call induced magnet. They behave like induced magnet. That magnetism is transferred to this one now start behaving like the induced one, and then be transferred to this one behave like the induced one, and then be transferred to this one. Is that okay? So we say magnets are made by magnetizing magnetic material. You just take magnetic material, you magnetize them. Okay, this is how you make magnets, especially temporary magnet or permanent magnet. The process of magnetizing a magnetic material is also known as magnetic induction. The process of magnetizing a magnetic material, you need that definition. What is magnetic induction? It's the process of magnetizing a magnetic material. The process of magnetizing a magnetic material is known as magnetic induction. Now, when unmagnetized paper clip is brought near a magnetic bar, or a bar magnet, it is attracted to the magnet. It is attracted. This happens whenever we have this situation, we say that the paper clip has become an induced magnet. And this induced one is in turn transfer this magnetic behavior to other paper clip. Okay, so that's the whole process is called magnetic induction. Okay. Okay, now let's take a look at. We say the process of induction does not require physical contact sometimes. So it's not like for magnet to be induced is that this iron this bar magnet is touching this iron. No, you just bring it close. This one will jump to clinch to it. This iron will jump to the magnet to clinch to it. Sometimes it may not even jump to clinch to it. Even at a distance, it can transfer. This one can transfer its magnetism or magnetic property into this magnetic material, So sometimes it does not require physical contact, as you see in this figure 50.6. Now the magnet can induce magnetism in the iron bar. This is an iron bar. This magnet can induce magnetism in this iron bar by what? By simply being brought near to it, by simply being brought close to this bar magnet. So you bring a magnet to this iron bar, then this one is able to transfer the magnetic property or magnetism into this one. Now the north pole of the bar magnet induces a south pole in the near end of the iron bar. This one, the north pole, will induce south here. The north pole here, the north pole of the bar magnet induces a south pole here. Induces a south pole in the near end of the iron bar. And the north pole in the farther edge. So it induces a south here and induces north on the farther edge because of magnetic attraction that will exist between this magnet and magnetic material. Okay, now let's look at that simple phenomena of magnetism. What happens? Now this is just a magnetic material. Okay, if you take a magnetic material, what do you see? Magnetic material can be magnetized because of the presence of what we call the magnetic domains. Okay, there are domains within. If you take iron, there are domains within the irons. Okay, like different segments or different regions. What we call magnetic domain in any magnetic material. The different segments or different regions are called the magnetic domain. For example, here is a magnetic domain. This place is a magnetic domain. This whole place. And then also this place is a magnetic domain. This one, with its O arrow, is a domain on its own. It's a magnetic domain. This place is a magnetic domain. Each one has its own north and south pole. Remember the one with the arrowhead? The arrowhead is the north. The other side is the south. The arrowhead is the north, and the tiny end is the south. Okay, so these are different regions of the magnetic domains. So we say magnetic material can be magnetized because of the presence of magnetic domains. Each domain behaves like a small magnet on its own. Each domain, if you take this domain, if you cut it out, it's like a small magnet. This one is like a small magnet. Why? Because it has south, north, or north, south, with these arrows. North, south, north, south, north, south. Each one behaves like a small magnet within its own capacity. And we can represent them using arrows as we've shown. You can see the arrows. Okay, the arrow is showing the north. This arrowhead is the north, and this other small end is the south part of this. Okay, the arrowhead will show north, and the other side will show the south. Okay, now let's take a look at the characterizations of how magnetism is being flown or is being introduced to a magnetic material. You know, naturally, a non-magnetized bar has its domain in various orientation. You can see this one is going this way, this one going this way, not arranged like this. This one is the one that is already magnetized. This one is like the one that is already magnetized, right? This one is the one you can see all the arrows going the same direction in a straight line. But like this one, in an unmagnetized bar, you can see each magnetic domain has its own behavioral pattern. Meaning, you can see the north is going this way. Here is the north for this one. This way is the north for this magnetic domain. And here is the south. This way, the north is going up this way. And the south is from here. You can see the behavioral pattern is different. This one is going down. The north is going down. And here is the south. So every domain, the north is going this way, down this way to the left. And the south is here. So you can see this is what we call the unmagnetized steel bar. Unmagnetized. It's not magnetized yet. So it's like when you say the net force is 0 or the net magnetism is 0. Okay? So here, it's not a magnet yet. It's just a magnetic material. It's not a magnet. You can see everything is not flowing in the same direction. So it's not a magnet. So the magnetic domain in an unmagnetized bar points in random direction. You can see in random direction. Very random direction. These ones are pointing in very random direction. Right? Okay. So that's what we see in the first case here. Now let's see the next case. The north pole of the bar is placed on the left of the unmagnetized bar. So we bring a magnet now towards this one. We bring a magnet to it and place the north pole of the magnet. It will be placed on the left side of the unmagnetized bar. On the left side, we place this one here, the north pole here. So when we do that, what happens? We see realignment. We see realignment. Even though it's not completely shaking yet, you can see realignment. You can see each domain is pointing in the same direction now. Like, even though not perfectly in the same direction, but they are being aligned. You can see all north is this way because the arrowheads are all on this side. All the arrowheads are pointing this way. So you can see it's being aligned, all the north here and all the south this way, all the south. Here south, and here north. For these domains, here south, here north. So they are aligned. Now we say the magnetic force from the magnet causes the south poles of the domain near the magnet to be attracted to the magnet. So all other domains rotate and point in that same direction, producing a net magnetization. All the other domains will start to point in that direction, thereby producing a net magnetization. Okay, we say each arrow is arranged directly behind the arrow in front of it, right, to produce a net flow of the magnetism, right? Therefore, the north poles are cancelled out by the adjacent south poles. The north poles are cancelled out by the adjacent south poles. Now, the tiny magnet, this place at level 5, this level 5. What's the explanation between here and here? In level 5, we say the tiny magnets at both the ends are free. The tiny magnets from both ends are free. Now, this produces the effect of the north and south. This produces the effect of north and south, or north or south poles at the ends. Now, this allows the magnetized bar to behave like a magnet because you can see the beginning as south pole, the end all are aligned as north poles. So this will make this one to start behaving, this unmagnetized steel bar, because we brought a north pole magnet towards this side. If you realign them, and you see at the end of the day, we have the magnetic material behaving like a magnet. Now, the tiny magnets at the ends tends to fan out due to repulsion force between the like poles. Due to repulsion force between the like pole, it will fan out because this end north will be attracted to this end north, and then they will be repelling. This domain will repel. You can see it's not straight. This one is moving this way, this one moving this way. Why? Because there is a repulsion force between them. But if you see the middle, they are not fanning out. This is behaving really like a magnet at the middle. At the beginning, there's an attraction, a repulsion or attraction force. At the beginning, in the end, there's a repulsion force in the end. Now, what can we do with what can we do with permanent magnet and electromagnet? Here, we are talking about uses. Here, we'll be talking about the uses of permanent magnet and electromagnet. Okay, I think before we talk about permanent magnet and electromagnet, let's talk about temporary and permanent magnet first. You know, at the beginning of the video, I briefly talked about temporary magnet. I said a good example is iron. Iron is used for making temporary magnet. Why? Because it can easily be magnetized and it can also easily lose its magnetism. It can easily be magnetized and it can also easily lose its magnetism. That's why iron is used for making temporary magnet. That's why iron is used for making temporary magnet. Is that okay? Now, for steel is very difficult for it to be magnetized. The steel is very hard. Okay? Steel is magnetically hard. Steel is magnetically hard. It's very difficult for it to be magnetized. A magnetically hard material is difficult to magnetize, but once it is magnetized, it retains its magnetism afterwards. It retains it. It stays magnetized for a very long time. It stays magnetized for a long time. Now, this is the difference between soft iron and steel, which is hard material. steel is magnetically hard. It's used for making hard permanent magnet, while soft iron is soft. And why do we call it soft? Iron soft. Why do we call it soft iron? Because it can easily be magnetized and can easily lose its magnetism. That's why we call it soft. Not because if you touch it, it's soft. Not because when you touch it, it's soft. No, iron is not soft. We call it soft iron because it can easily be magnetized when you bring a bar magnet towards it, and it can easily lose its magnetism. For example, what I mean is that if this is steel, let's say this is a steel, and then you bring a bar magnet towards it. This bar magnet has a south and north. Let's say here is south and here is north. Sorry, here is north of the bar magnet. And then you bring it to, let's change color for this one. You bring it to this iron. You bring it, it will transfer its magnetism, right? To transfer its magnetism to this iron. To transfer its magnetism to this iron. Now, this iron will be able to trap magnetic nails. To be able to hold on to nail, attract nails, or any magnetic soft made of iron, paper clip, anything. It will be able to hold on to it. Okay. Now this is when you put the magnet on top of it. For steel, the same thing. Let's say you bring a bar magnet. Let's say you bring a bar magnet. This is south, and this is north. This is south. The top one is south. And then let's say you bring, let's change the color. Let's say you bring steel. You bring steel here. Magnetism will be transferred here, right? By induction. Magnetism will also be transferred here by induction because they are magnetic material. This is a steel. You bring a steel here. You bring a steel here. Okay, it's laggy, so you already know what I mean. This steel, this iron. Okay, so this one will also hold paper clip or whatever you bring here, it iron, nail, clip. It will also attract them. Okay, but the moment you take out this bar magnet, all this one will fall off for soft iron. It's easily magnetized, able to pick more nails. This one pick only few nails. This one steel is difficult to magnetize. This steel is difficult to magnetize. So it will not pick as many nail or paper clip as soft iron. The steel will pick only few paper clip, not as much as that of soft iron. And the moment you take out this one, the moment you take out the bar magnet from touching this, all the paper clip or nails that we attracted here, all of them will fall off. The moment you take out this one, all of them will fall off. So it easily magnetized. That's why it could take so many iron or paper clip. But when you remove the bar magnet, all of them will fall off. All of this one will fall off. Also, meaning it's also easy to lose its magnetism. That's why it's soft iron. This one is a soft iron, easy to magnetize, so it's able to attract so many paper clip. And when you remove the bar magnet that is providing the magnetism, all this one will fall off, meaning this one will lose all its magnetism. This soft iron will lose all its magnetism. All this paper clip will fall off. Unlike this one, okay, this one will only attract few paper clip or nails. Now, when you remove the magnetism, all of them will not fall off. Some will fall off, some will still remain. Because steel is used for making permanent magnet. It's used for making permanent magnet. So not all of them will fall off. Some will fall off, some will still remain. So because of that, we say steel is used for making permanent magnet. Is that okay? Now, so this in conclusion, we say that because they can ask you to describe an experiment to explain this, I'm explaining an experiment in the exam, paper 6 or paper 4. Now, so we say that the different magnetic property of soft iron and steel, they are summarized. We can summarize them, right? the properties of soft iron. Number one is that for property of soft iron, it is easily magnetized to become a stronger induced magnet. It is easily magnetized. Property of soft iron. It is easily magnetized to become a stronger induced magnet. So this one can easily be a stronger induced magnet, easily magnetized. The second property of this one is that it loses its magnetism easily. The moment we remove this iron bar, it will lose its magnetism easily. So these are the properties of this soft iron. Easily to magnetize to form a stronger induced iron, a stronger induced magnet, and also easy to lose. It easily loses its magnetism the moment we remove the bar. Now, what are the properties of the steel? What are the properties of steel? Magnetic properties of steel. It is difficult to magnetize. The steel is very difficult to magnetize. Hence, it becomes a weaker induced magnet. Because it's difficult to magnetize, it's a weaker induced magnet, meaning it will only be able to attract only few nails, only few ones. So it's a weaker induced magnet. It's not as strong induced magnet as this one. Because this one is a stronger induced magnet, it's able to attract so many nails to itself. As long as this one is on top of it, it's touching it. But the moment you take out this one, you take out this bar magnet, all the soft iron will lose its magnetism and all these nails will fall off. But this one will attract few ones. But when you take out this bar magnet, all of them will not fall off. Some will still be stuck to this one. Only few ones will fall off. Okay, so it's also difficult to lose its magnetism, this steel. It's difficult to magnetize and also difficult to lose its magnetism. Now let's go to uses of what we do with permanent magnets and electromagnets. Like we are saying, in this case, like we are saying the uses of magnets and electromagnets. It's like we are saying the uses of magnets and electromagnets. The first big use we can put, you see, uses of permanent magnets. The first big use we put magnets to is the magnetic door catches. If you open your refrigerator, you know, when you close it, it's like being attracted, stuck to it. When you close the door, the refrigerator, when you close the door, it will, like, it's a magnetic operation. It will stick to the door, right? You can go to your refrigerator, open it and close it. You see that it will, as if it's like attracted to it and stick to it. Okay, that's why the refrigerator doors do not open easily. Here, we put kind of magnetic material. We use a magnetic property, magnetic bar, to make this edge so that they will be stuck to this magnetic material, to be attracted to magnetic material. Put magnet in here and put magnetic material in here. So when you close it, it will stick to it. So we say the magnetic strip made of permanent magnets, they are fitted to the door of a refrigerator. When the door is closed, the attraction between the magnetic strips and the steel frame keeps the door closed. Okay, this one uses of a permanent magnet and electromagnet. Another one is the maglevs. I think at the beginning of the video we talked about the maglevs, magnet trains. Now the train, you see this fast-speed train, they run on train track. Now the magnet, there is a magnetic magnet. This train track, they are made of magnet, maybe steel or iron. They're made of magnetic material. Why this has some magnet in it? Now the train do not touch the tracks, so there exists a frictional force. To reduce, frictional force is reduced. Okay, frictional force is reduced as it moves. So to enhance the speed of the train, that's how they were able to develop a fast-speed train, because of magnetic levitation, what we call magnet. Magnetic levitation is used trains, okay, is used in trains, and they use magnetic attraction and repulsion to levitate and move forward. Magnetic attraction and repulsion. There's an attraction repulsion between the train and the train track. Attraction repulsion. This speed train is made not to directly touch. There's a magnetic attraction repulsion between the train and train track to keep the train on the fast speed, and this reduces friction. And the frictional force that is reduced enables the train to move at a very high speed. So this magnetic levitation is what we call magnet. And this is one big application of magnet. Another big application of magnet is the use of electromagnet. Electromagnet is used to separate magnetic material from non-magnetic material in a dump site. In a dump site, okay? When you bring a tray, you can bring a tray with electromagnet hanging on it to pick some magnetic material like iron and steel and cobalt and nickel that are put in place on a dump site while leaving the non-magnetic material. Okay, so these are three big uses of this. Now let's go to the final stage, which is you can pause the video and solve these questions. Okay, you can see iron tracks that are this metal. This is a bar. This was the one I was explaining, earlier on. Okay, this is a bar might touch it. This is a metal, and this nails are being attracted. You can see so many of it. Since you see so many of it, it means this is iron, a soft iron, because it have induced magnetism. Magnetism is very strong. While this one few ones, it means is steel. This one metal 2 is steel. See, they can ask you in multiple choice exam. Metal 2 is steel because it attracts only fewer nails or magnetic or paper clip. Then the third one could not attract anything. It means this is not a magnetic material. It could be copper or magnesium or zinc, whatever it is, but it's not a magnetic material. Okay, so this one can be given to you. So pause this video and I think I have answered this question for you. Now let's go to what is a magnetic field. Let's end this chapter with magnetic field. What is a magnetic field? Okay, every magnet has a region of space. Magnetic field is a region in space where the magnet experiences a force. A region in space where the poles of the magnet experiences a force. Okay, you should be able to define the meaning of magnetic field. A region in space where the poles remember to measure the poles, where the poles of the magnet experiences a force. A region in space where the poles of the magnet experiences a force. So every magnet has a region of space around it called the magnetic field, the region. Like this kind of region. These are the poles, the edges. These are the poles, the edges, okay? These poles, you can see it experiences stronger force. Why? The tinier the lines, magnetic field lines, the stronger the force. The closer the magnetic field lines, these field lines, they are closer at the region. But here, at this other edge, they're very far apart. The field lines are farther apart. But at the edges, they are closer together. Means there's a stronger magnetic force. Okay, also here, same thing. We call the edges, the North Pole and South Pole edges. So here you have the magnetic field lines are very close together, and you can see that you have a stronger magnetic field. So magnetic field lines, and if you're asked to define magnetic field, you say magnetic field is a region in space where a magnetic pole or where a pole experiences a magnetic force, where a pole experiences a force. You can see this bar magnet placed on the Earth and showing the magnetic field lines. Okay, the Earth is a giant magnet. The Earth itself is a giant magnet. The Earth itself is a giant magnet. Remember, magnetic field lines emanate from the North Pole and terminate at the South Pole. Magnetic field lines, they are represented by dashed line, and they start from the North Pole. All magnetic field lines start from the North Pole and terminate at the South Pole. They start from North Pole, terminate on both sides. They start from the North Pole, terminate at the South Pole. Start from North Pole, terminate at the South Pole. Start from North Pole, terminate at the South Pole. Start from North Pole, terminate at the South Pole. Till this is how we represent it, okay? Now let's move on to still explaining the magnetic field. I already defined it. So we say a magnetic material or a magnetic pole placed in the magnetic field will experience a force, or what you call a magnetic force. So we've learned this before in earlier parts, and that a freely suspended magnet points in the north-south direction. A freely suspended magnet points in the north-south direction of the geographical Earth. Point in the north-south direction of the geographical Earth. So as the freely suspended magnet is placed in the magnetic field of the Earth, the magnet experiences a magnetic force from the Earth. The magnet will experience a magnetic force from the Earth. Because this bar magnet, this is the north of it, and this is out of it, and while the Earth, this is the north, and this is the south pole of the Earth. Is that okay? Now let's move on. Here is an experiment It's an experiment on how we can visualize the magnetic field of a magnet. How we can visualize the magnetic field of a magnet. Okay, what this one just means, how we can obtain the magnetic field. These field lines that we talked about, these field lines, these are called the magnetic field line. So, they are not visible. When you take a magnet, you don't see any line like this around it. You can't see it. They are invisible lines. So how do we come about it? We can use, there are many ways to do it. We can use iron filings. We can bring a bar magnet, put iron filings, spread on a piece of paper. Okay, let me tell you a shorter one. A shorter one compared to what this material has. Okay, you can take iron filings, sprinkle them on the plain white paper on the board or a cupboard on your bench, and bring a magnet and put a magnet within the iron filing. You see all the iron filing we align like this. All the iron filing we align like this. All we align like this. Showing you that the magnetic fields are like this. Showing you that the magnetic fields around the bar magnets are like this. Iron filings. You know iron filings? When you take a sharp cutlass and you take a file, you sharpen the cutlass, there are small filings that will fall out. Gather them, take them, spread them on a cardboard or a white paper on the bench. Then bring a bar magnet and place it on that paper. You see all the filings we align like this. All the filings we align like this. So this one experiment to demonstrate it. Or we can follow using a compass needles. You bring a compass needle near a bar magnet. You locate the knot of this one, and then you bring a compass needles, and then you mark the first knot of this compass, because the knot of this bar will be the knot of this compass. You mark the first knot, you shift it, you mark another knot, you shift it, you shift this compass needle, it will point the knot, it will show you the knot again. You mark it, you shift it, you mark knot, and like this till you get this behavior. So you should be able to explain this in the exam, either paper 6 or paper 4, and how we can. So at the end of the day, when you repeat all these steps continuously, you get this kind of magnetic field line, starting from the North Pole to the South Pole on both sides. North Pole to the South Pole, North Pole to the South Pole, and then North Pole. This one is as if it continued. We now show how it's entry. Then the one that is straight like this, we show that it's entry like this. Okay, so on both sides, the same behavior. So we can conclude that the magnetic field lines appear to leave the North Pole and end at the South Poles of the magnet with a pattern similar to what we have seen in the previous part. So I think with this we have come to you pause this video and solve this particular question. With this we come to the end of our today's class. Thank you for joining us. Thank you. Okay.